do Friedrich Anders, vulgo Frederico. Parece sempre um Frederico aí. O Friedrich é lá do AIP, Potsdam, e vai falar para a gente hoje tudo que você precisa saber sobre APOGEE, arqueologia da galáxia e asteroseismologia. Tá? E café também.
Café? Sim. Você já viu. Okay. So I'm not going to talk about. I'm not going to talk as a single person. I'm going to talk for a big collaboration, because nowadays we cannot work alone anymore. So if I will go back to the first slide, my work is related to many other people's work, and so they are also equally important. And okay.
You can use the person.
Okay. All right. And to say a little bit about myself, I'm from a small shanty town in eastern Germany. You can see here, it's called Dresden. And then when I fell in love with astronomy, I had to move away from this place, and went to Potsdam to do my master's thesis with Christina Capini and Matthias, and I also continued there for the PhD. And also,
so that's the IEP?
That's part of the IEP. See, that's the Einstein Tower. Was built in 1922 to test the theory of general relativity, and it's the only expressionist architecture in Germany. Of course. And it has to be renovated every 5 years because it falls apart. Yeah, it's very nice, and it's a solar telescope, so.
I don't know windows.
Windows. So the light enters here, and then the spectrograph room is in the cellar.
So where's your office?
My office on another campus.
Oh, okay.
On another hill. Okay. So today I chose the title APOGEE, Archaeology and Asteroseismology because our begin with A, and Brazil deserves a AAA rating at least once. But I'm not going to talk about this in this order. I'm first going to talk about archaeology, then about APOGEE, and then about archaeology. Okay, so what is galactic archaeology? We basically want to find out how the Milky Way was formed. Pretty bold question, and the way we can attack this, rather also philosophical question, is we have to simulate a Milky Way-like galaxy and then compare to observations. So the simulations are pretty detailed. You can follow everything that's going on in the galaxy, and the observations, in turn, they are difficult. Right? You cannot measure accurate distances. You cannot measure accurate movements. Chemical abundances are difficult to obtain. So this is an ongoing project. It will be ongoing for more than 20 years, I think, from now. And the problem is similar to the problem that you have when you are inside a coffee cup and you want to know how this coffee was formed, how this coffee cup configuration was formed, who poured the milk inside the coffee, and how much milk, with which velocity, if the coffee is an espresso, or if it's a Turkish coffee, right, if there's dust inside the galaxy, and so on. But the problem is even more complex, because the cosmic cloud can be moving, and it can form stars. And yeah, there can be other stuff falling into the cup. So now imagine you sit inside this cup and only have one picture. You cannot follow any evolution. You just have one picture. It's extremely difficult to say something about. So the basic idea of this new science of galactic archaeology is a combination of chemical evolution theory that is more than 50 years old with stellar dynamics and cosmology. And to use empirical relations as well as forward modeling techniques, which means that you take a model and make mock observations of this model to constrain the model parameters. And this involves all observational techniques that you have at hand in astronomy, spectral analysis, photometry, and astrometry. So, and the main driver for the community to move away from a simple chemical evolution, models was the discovery of the strength of radial migration, so that stars move away from their birthplace and lose the information about the kinematic information about their birthplace. And yeah, this can happen through various processes: interaction with the vast spiral arms, or merging and internal heating. So the problem is essentially this: you observe these things here in the lower panel of the plot: velocities, proper motions, parallaxes, magnitudes, and spectra, from which you derive these stellar parameters for a considerable sample of stars, say a couple thousand, and then you want to say something about the disk structure, the dust, star formation history, initial mass function, and all this stuff. Okay. So you have to go to these intermediate processes. One of them is to determine the ages of stars. Okay, so going back to the models, these chemical or thermodynamical evolution models of galaxies, they make predictions in this high-dimensional space. They predict the distribution of stars inside this H kinematics composition hypercube. Right? Now, okay, so this cube is of course more than three-dimensional. So it's 6 plus 20 plus 1 dimensional at least. So the basic problem, as I see it, is dimensionality reduction. We have to look for the most robust slices of this hypercube that can constrain chemical models or thermodynamical models. And one example, a historical example, is the thin and thick disk controversy that is still not resolved. Basically, the problem is that from star counts, if you look towards the northern galactic pole and count the stars, then you can fit this star count profile by 2 exponentials. Okay, a thin disk and a thick disk. And then the question was, okay, why is this two exponentials? And do these 2 exponential disks have different chemical properties? Okay, in 1998, 1996, people started finding out, okay, the thick disk has actually high alpha abundance, and the thin disk has low alpha abundance and higher metallicities on average. So the idea was maybe these two disks were formed separately in time. This was the idea from Justina's 1997 model. The thick disk was formed early on from hot gas. So that the stars are also in hotter orbits, and then the thin disk was formed gradually by infalling gas that cools, and then gradually formed the thin disk. But nowadays, okay, so these are typical slices through this hypercube. But nowadays, it's not clear whether this profile can be actually fitted by many more exponentials. Right? Can also fit it by 10 exponentials. So maybe it's just a gradual transition, and this gap that you see here is not necessarily there. So that's an ongoing controversy. So the idea to resolve this was to take many thousands of spectra of stars throughout the Milky Way, if possible. So the era of spectroscopic surveys started with the Geneva Copenhagen survey of the solar neighborhood, where 16,000 stars were observed in the Hipparcos module, and then shortly afterwards the Rave survey started to observe more than 500,000 stars outside the Hipparcos volume, so at a distance of 3 kiloparsec more or less. And this is where the whole thing of galactic archaeology with stellar spectroscopic surveys started.
Lamos is actually working.
Lamos is working. Lamos has taken more than 1 million spectra already. The conditions are extremely bad there, but when they can observe, they observe, I think, almost 2,000 stars at once. So it's a very efficient machine they have. Okay. So APOGEE, as probably most of you know, was initially a 3-year spectroscopic survey at the APO in New Mexico, and was the first ever multi-object fiber spectrograph in the near infrared. And I think KMOS is going on too. But okay, it takes high resolution spectra. It's a high signal to noise, primarily of red giants in the H band. And it's also a very efficient radio velocity machine. So it can deliver precise radio velocities, about 0.1 kilometer per second. And abundance of chemical elements, I think more than 15 now. Okay. And this was the first light plate of APOGEE, cluster field. I can see where the fibers were put. And this is what the spectra, 2D spectra look like, false color. And also, if you just want to take a look at some random stars, you can go to this website and enter TUMAS ID, an APOGEE ID, and look at the spectra, zoom in, zoom out. Very nice tool. And this, okay, so this is for the public part, for DR12. So in DR12 there are already a bit less than 100,000 stars included. And all spectral products, from the raw spectra, calibration, up to stellar parameters and chemical abundances. So we'll just show two results actually from the APOGEE survey that are relevant in terms of galactic archaeology. One was this, where we looked at my diploma thesis. Actually, I had the luck to be one of the first to look at the year 1 data of APOGEE. So we decided to make this plot where in the top row you see the data that existed before APOGEE, from 2011, for the inner galaxy, solar neighborhood, and outer galaxy. So this is alpha abundance versus alpha over I versus I. Okay. And here they conjectured that the high alpha abundance cloud disappears as you go outward. But based on a couple of stars only. And then with APOGEE we had observed already thousands of stars in each of these bins, and you can see a lot better what's going on. And indeed, the thick disk, chemically defined thick disk, dies out as you go to the outer disk, and also the metallicity distribution peak of the thin disk, which is supersolar in the inner regime, and the round solar in the solar neighborhood, also becomes more metal poor as you go towards the outer disk, which is essentially a signature of inside-out formation of the galactic disk. So all this is relatively model independent, right? And also this paper from Haley 2015 is not based on any models, let's say. This shows the metallicity distribution functions at different galactocentric distances. So yellow and red are outer disk, and black and blue are inner disk. You can see how the metallicity distribution changes first of all the peak, and then also the skewness as you go from the outer to the inner disk. And these authors identified as a signature of radial migration. The change of the skewness parameter here in this distribution. And it's still not clear whether this is actually an observational bias or not. So this is ongoing work. And okay, so these three panels are close to the plane, and then as you go higher above the plane. And you see, as you go higher above the plane, the metallicity distribution is essentially not varying anymore, which means that the thick disk is not so much different in the inner disk than from the outer disk. Okay, so now one of the most crucial parameters in thermodynamic evolution models is age. If you plot this prediction space like this, and of course, if you want to test these models even further, then you have to try to determine stellar ages and then compare. So now I come to the next part, which is ages and asteroseismology. How do you determine ages for stars? It's a long story. Basically, all the history of astronomy was accompanied by the question, how old are the stars? So there are different ways to determine ages for stars. Stellar activity is one. It's one widely used tool. Gyrochronology, which measures, so there you measure the rotation of stars, and then for dwarf stars we know that the dwarf stars become slow rotators during their lifetime. You can calibrate with clusters, and lithium depletion boundary is another tool that's only applicable to young stars. Then for very old stars and metal poor stars, you can measure the uranium to thorium ratio, and this gives you a direct age indicator because you understand the nuclear physics that describes uranium-thorium decay change. And also you can use stellar kinematics as a proxy for age. But the most widely used methods are Hertzsprung-Russell diagram methods. Basically, you compute theoretical isochrones and then compare the position of a star in this diagram with the isochrones. And you can also do detailed modeling of the stellar structure if you measure accurate oscillation modes of the star. Okay, so here on the right hand side, this shows typical age probability distributions when you use color magnitude diagram methods. Okay, so you can have stars with one well-defined peak. You can have stars that you can not say anything about here. This rosé curve. You can see stars that are young, or you can have stars that have a double peak HPDF. And particularly interesting for galactic archaeology are red giants, because they are very luminous, they're very bright. You can and they have solar-like oscillations. Okay, and from the solar-like oscillations, they're excited in the outer atmosphere of the star, and then they propagate through the star, and they give you if you take a light curve and then make a Fourier spectrum of this light curve, you can get information about the extent of the star, the stellar radius, and the mass. And but you need ultra high precision photometry to detect these oscillations, typically millimagnitude. So this means space missions in almost all cases. And but once you build such a satellite, you can take oscillations of these stars to distances of kiloparsecs. Okay, so basically there are scaling relations between the radius and mass of the stars and parameters that describe the frequency spectrum. Yeah. Okay, and what you get out from this are radii typically to 5%, masses to 10%. If you have a good, well-measured spectrum. And you can measure these two parameters, main parameters that characterize the frequency spectrum for large samples of red giant stars. And then another thing is that once you have the mass, you can get the age, at least for red giants, because, yeah, just because you know when a star is on the red giant branch, it must have lived for some time. Okay, and if you add spectroscopic constraints like spectroscopic temperature and metallicity, then this relation becomes even tighter. Okay, this is log age versus mass, so it's not so tight, but for each metallicity, if it's well defined, then you have this well defined relation. And this is the distribution of currently observed seismic samples in the Milky Way. So here's the Sun, here the Corot fields, and this is the Kepler field. right now Kepler-2 is observing many more fields. So the idea to use astroseismology in combination with spectroscopy for large populations of red giants was born, I think, in the late 2000s, when there were two conferences, one in Rome and one in Sesto. And last year we had a follow-up conference in Bad Honnef in Western Germany, where Christina got, essentially she got a lot of money and then she invested in this conference. It was very, very fruitful conference. And yeah, so there we discussed all the problems from the stellar modeling problems up to the data analysis, spectroscopy, and also the analysis problems, higher level analysis. Let's see. Okay, so for APOGEE has cleverly observed the two main Poirot fields and also the Kepler field, so that this experiment is essentially ideal to use these three samples to study relationships that involve the aging stars. And so for my PhD thesis, I'm focusing on the Poirot part, Poirot APOGEE sample, which, if you break it down, it's only 700 stars. From the 100,000 APOGEE stars, only 700. But these are very precious because we have some age information. Okay, so this is again the distribution in R and Z and X and Y. And then comes the part where Thais and Leo are most heavily involved. They compute from the seismic and the spectroscopic data the radii, masses, and distances. Okay, so they have this param pipeline that is essentially a very high-level isotron matching code. So you compare the data with isotrons and find the best matching stellar models. And the typical age uncertainties that you get out are 25%. Usually, if you don't have astroseismic information for red giants, the age uncertainties are 80%. So this is sounds bad, but it's very good. It's actually very good. And the distances that we get out in the extinctions are very precise. So distances to 2%. Better than most Hipparchus distances. Okay, this is how the HR diagram looks when you just take spectroscopy, spectroscopic information, and then here you add the log G from Poirot, which is extremely precise, and then you start to see more structure in the Hertzsprung-Russell diagram. So here the red clump appears very distinctively at a secondary red clump here, and yeah, and also the pipeline can exclude some stars that lie us in unphysical parameters space. So, but
can I go back? The diagram on the right seems more scattered. Is that expected? I mean, you are resolving population. Is that what you're doing?
Yeah, I think it's actually expected to be more scattered than this. This might be an artifact of the pipeline of APOGEE, that it just, because there's a degeneracy between effective temperature and surface gravity the spectra that is not entirely resolved.
Okay. Do you know why you have unfeasible solid particles?
Because I think most of them are related to noisy light curves, and then you start to measure frequencies that are not actually there.
Aliens.
Aliens. Yeah, but the pipeline detects these guys and goes them. Yeah, the light curves of Corot are not ideal. They're not comparable to the light curves of Kepler. Kepler observed for 4 years, 5 years. In Corot, this was just 3 months. Okay, what we get out in terms of age is, okay, here on the left hand, I plot HPDFs, all the 690 HPDFs in bins of the maximum age of each PDF. Okay, so the young stars are here, and the older stars are here. So typically, what you see is that for the older stars, also the PDFs become very, very widespread. So it can even be that this star that has a mode age of 11 or 12 gigayears is actually 4 gigayears old. But on the other hand, if you measure that the star has a mode age of less than 0.5 gigahertz, it's impossible that's older than 2. Okay. So at least is something. Okay, and then this is just a Hertzsprung-Russell diagram indicating where the multi-peaked PDFs occur. And of course, this is in the places where you have red clump and red giant branch very close to each other on the isotope. Okay, but now we can use these ages of these HPDFs to compare to models. Okay, what do the models predict? For example, for the dependence of magnesium over iron versus age. So this model from Christina was just it's a usual model. Everyone has this kind of model in the community of galactic chemical evolutions. So you can simulate a thick disk, all thick disk, and then the thin disk, and because supernovae type 1a start to explode at some point, this ratio magnesium to iron will be lowered over the course of time. Because in the beginning, you will have a lot of supernovae type 2. These come in magnesium, not so much iron. Then a lot of iron is produced, and this ratio declines. Okay, and this model, the specialty of this model is that she computed it for very for the outer disk for rings centered around the galactic center. Okay. But okay, so in this part there shouldn't be anything. But now when you compare it to data, actually there are stars that are young and enriched in alpha elements. And so this was the first data that we did on this. With this sample, we looked at magnesium alpha over iron versus age diagram. Also in the literature, we found some stars that are unexpected from canonical chemical evolution models of the disk. Now the number of these stars is low, usually. In the solar neighborhood, it's also low. But when you go to the inner disk, you look into the inner disk field, and very much inner disk indeed, then you start seeing a lot more of these stars. So this was very intriguing, and it shows also that it cannot really be a flaw in the method we're using, because then there's no reason why the outer disk should be different than. So then we started to rave about possible explanations for these objects, but there's no conclusive evidence. So maybe these stars can be formed in star-forming bubbles, so where you have a lot of star formation in a short period of time, enrich the interstellar medium with type 1 and type 2 supernovae, so with magnesium and other alpha elements, and then if the gas continues to form stars, these new forming stars will have enriched magnesium to iron. But also, there could be debris from a massive satellite galaxy, okay, but we don't see any massive satellite galaxy, or at least the remainders of it in the last couple of giga-years. And also, there's the possibility to form exotic chemistry stars from close binaries. Okay, then one other paper that we're currently writing is we can actually look at the time evolution of the radial abundance gradient, metallicity abundance gradient in the thin disk. So we bin this diagram, iron versus galactocentric radius in small bins or larger bins in age, and then look how this diagram evolves with look back time. Okay, these black dots here are Cepheids. Cepheids are more or less 100 million years old, and the green dots are clusters for which you also know the age, and then some other samples for which age has been computed, and the blue are our data. And interestingly, I mean the slope doesn't change much of the gradient, but the scatter increases. And this might be a signature of radial migration, early mixing plus radial migration. And maybe this is a way to quantify the amount of radial migration. Okay, so yeah, as you can see here that the slope is not varying too much, but the scatter is.
So what's the gap in you're not surveying something?
The gap? Yeah. Okay, so the gap is the solar vicinity.
Okay.
Yeah, we look into the solar vicinity. We look into the outer disk and the inner disk, and then there's a gap in between close to the sun. And then we're also looking at the alpha over iron versus iron diagram as a function of at different galactocentric distances. Maybe I have it here. Okay, so this is alpha over iron versus iron for 5 different bins in galactocentric distance. Okay, so here's outer disk, inner, and then here you go inner, 4 to 5 kiloparsec, here 11 to 14 kiloparsec. Now, the dots are colored according to age. Blue is young, yellow is intermediate, and red is old. Okay. Now, what's nice here is that in the outer disk we have almost only young stars. And then, okay, then in the inner disk we have these weird blue dots. And then we can compare this to a model. Now this was the most difficult part. This is the thermodynamic model of Ivan Minchev and Christina. So the pure chemical model are these lines here, and the shaded colors, and below there's this gray stuff. These are the model particles. And then we made a whole mock procedure to observe a Corot apogee-like sample from this model, and also simulate the age errors. This was very non-trivial. And what we get out is this. Yeah. So, and here it shows where the model, in particular this model, which was previously it was shown that it matches many observables, right? Matches this observable, the metallicity distribution function perfect. We can match the gradients, we can match anything, and now we start to see some very clear differences between the model and the data. For example, now in the model you have this decline of magnesium versus iron all the way up to high metallicities, whereas in the data there's flattening, banana shape. This is related to stellar yields and details in the nucleosynthesis. But then other things like the age distribution, for example, in each bin, they are not so dependent on the details of the chemistry. So this is very new. And in summary, I just wanted to show you that combining this so-called entry-level seismology, because we don't use the full frequency spectrum of the stars, of these red giants, just the two main parameters, which characterize the mass and the radius. If you combine this with spectroscopy, we can get more precise ages, but we have to be careful when interpreting small subsets. So it's a statistical method, and it only works for statistical samples. And systematic uncertainties are also a bit difficult to estimate. But even considering this, we can put new constraints on thermodynamic models and tell where the models fail.
So how are we going to move forward?
Yes. Well, there's the idea to use the K2 field, where APOGEE also observed, I think there's already a sizable overlap for many of the new K2 fields that have been observed. And so K2 is the Kepler-2 mission that moves through the ecliptic plane and stops.
This be a sizable significant use.
Yeah, the most interesting, most important parameter there is the direction which you look at, because there are some directions that are just not so interesting to look at. But there are some fields that are in the galactic bulge and also in the disk. But if you move too high above,
still down from the Apache.
Yes, but there are some part that will be observed there, which is out. Okay. And of course, so in the end, I didn't talk about APOGEE and Kepler, but there's also many things going on. The thing about Kepler is that it looks only in azimuthal and z direction. So here, this Corot sample can be used to probe the radial dependency of chemistry or whatever parameters in the galactic disk, whereas the Kepler sample is not so useful for that. It's been recently used to measure the age distribution with height. Yeah. And also, but I should say that this for Kepler, the Thais actually used Kepler to develop all these tools that we're using, and now also for Kobo. Okay, so now Apogee 2, look at a small look into the future. Apogee 2 is not future, it's already happening. But Apogee 2 North started observing in 2014, whereas Apogee 2 South is still being constructed in Las Campanas, and it will have a smaller field of view, so about half the size of the Apogee North fields, and also not so much time, because Apogee is supposed to end in 2020, so there's not so much time to observe all of these parts that will be covered by Apogee North. But still, the good thing is that we'll cover all the disk in the south, and some signs in the Magellanic Clouds. So you can also study asymmetries in the galactic disk using these two surveys together. And then I wanted to, I don't know, maybe want to brainstorm a bit with you what science goals BPG has for Apogee 2 and for Brazil, or what could be done better. So these are some of the existing projects that are already going on. So we want to make a detailed comparison with this Chiappini thermodynamical model using all Apogee data. And a similar project is also going on with Tridigal, where Tridigal will be compared to all the Apogee fields. And actually, Apogee can then be used to better calibrate the Tridigal model. And then, of course, Apogee will be important in conjunction with other surveys. So with Gaia, you will have very precise dropping motions. You can do kinematical studies throughout a large part of the disk. So before, there were just moving groups found in the Parker. Now you can go over kiloparsec scales and find moving groups and study the dynamical state of the disk and the spiral arm perturbations, this kind of stuff. So I think that Apogee will also be very important in this respect. Essentially because it delivers radial velocities out to further distances than Gaia. And then we're also involved in the preparing of the Plato mission. And yeah, but this is very much future.
Have you guys thought about how that's for most fit into this?
Well, for most, I don't know about this, but for most,
because that will be the right time. So I think conceptually, I think it's going to be a big segment. Yeah.
You think so? I thought it was more related to extragalactic.
Dark energy,
Okay.
right time to use
I didn't know that.
both extragalactic and slow.
Okay.
Just
But Formos will be different because Formos will be built upon the Gaia catalogs. So foremost uses Gaia as an input catalog. So it was essentially built to supply Gaia with radio velocity and low resolution abundances. And it's also not happening right now. It's happening in 2020 or so. And then, okay, then of course APOGEE has the capability to use 15 individual element abundances. So you can do a lot more there. And I think Kacha is involved in this, some of these projects. And okay, but on the large scale, one of the big ideas was to constrain the star formation history and radial migration history of the Milky Way a lot better than it's now known. But for this, I think we don't have the statistical tools yet to make this a compelling work. So it's really difficult. I don't know. And okay, so I mean, these are some of the projects that I know about. And then we'll say a little bit more about APOGEE and Gaia for the first data release, which will be coming this year. So there's one thing that is very interesting, namely the Tycho Gaia astrometric solution catalog, which will deliver parallaxes and proper motion with Hipparcos-like precision for 2.5 million stars, for the Tycho stars. And then, okay, for APOGEE, this means that there's an overlap more or less 30,000 stars. Half of them are giants, half of them are dwarfs, and this sample can be used to do chemokinematics outside the Hipparcos ball, and also it can be used to better constrain our distance scale of our spectrophotometric distances. So, if you're interested in using this sample, you can test any ideas that you have, science ideas that what you want to do with this sample already now, because we simulated what the sample will look like, and you can go to the track wiki and check it out.
This is already a simulation of the overlap.
Yeah. But just to show that people should be ready in advance for these big data releases, because then there's always people that are faster. Okay. I think this is the last.
Thank you very much. Thanks, Rich. Do you have questions from people attending remotely?
Well,
I have a lot of questions.
these Milky Way studies, what are the main source of contaminants? Some not stars. I mean, in your sample, does it get some extragalactic sources? What are the most?
No, so they are targeted based on photon, based on 2 mass essentially, and so you can exclude by color cards. You can exclude most of the extragalactic. There's just some. I think there's 2 or 3 weird objects that are the Red Square Nebula and some other. It's very, very clean. There are contaminants in terms of you want to target giant stars, but there's some contamination, 20%, 19% of dwarfs, M dwarfs. But these are interesting for other people, so it's not lost time.
I have a comment. I really would like to set up a meeting, go back to do this plans, to do the studies.
Yeah.
Yeah. If we're going to discuss those things, let's say, we could bring everything together.
Yeah.
Togetherness is the secret. And particularly interesting, the open code, training some of the population, the other ones are
Yeah.
Let's play, right? I don't know much about play.
About what? Plato. Plato is basically also a satellite that will be used to find exoplanets, and there's a small part from the stellar community that we
There's already flying.
no, also 2020.
So why are you treating that in Formosus of 2020 for black?
Yes, the 3 dots. Yeah.
No, I think because I would be interested in having Brazil participate in that.
Yeah. So I have completely
We have,
ignored.
supposedly we have one slot in that.
Okay. I have completely ignored that it wouldn't work.
So, anyone else has questions? Not just congratulations. When you finish,
This year.
when? This year is the
End of this year, so December. December. The plan.
life is a very big year, very beginning of this year.